Good day everyone and welcome to our next lesson. In this video, we will be talking about heat transfer by radiation. Let's begin. Radiation is the third mode of heat transfer that we have to discuss, and it is the most different since it does not need any media to propagate heat. Radiation basically allows heat transmission through the use of electromagnetic waves which do not need any matter to propagate. So radiation is the reason why the energy of the sun can reach the earth, okay? And since the mechanism of radiation is very different from that of conduction and convection, expect that our discussion here would be somewhat different as well. Let us first demystify radiation a bit by discussing what enables radiation. At the top of the lecture, I mentioned that radiation is made possible by electromagnetic waves, which can travel even in the absence of matter. This is what we call our electromagnetic spectra. It simply contains the different electromagnetic waves at different wavelengths. So we have from cosmic rays, gamma rays, X-rays, down to radio waves with the longest wavelength. Our rule of thumb for the electromagnetic spectra is the shorter the wavelength, the higher the energy of the wave. So we see here that cosmic and gamma rays are some of the highest energy waves in the entire spectra, while radio waves have the least power. Now, the light that allows us to see is part of this electromagnetic spectra, and it is part of a very thin fraction of it called the visible spectrum. The visible spectrum is what allows us to see colors. Throughout our discussion on heat transfer by radiation, or more commonly known as thermal radiation, we will mostly be dealing with electromagnetic waves falling under the ultraviolet, visible, and infrared spectra. Okay? Now, let's talk about the nature of radiation. Thermal radiation in our context is discussed in terms of the properties of a material on how it handles electromagnetic waves. Those properties are its reflectivity, represented by the Greek letter rho, absorptivity or alpha, and transmittivity or tau. These three parameters are related through this expression. The summation of those three parameters is equal to 1. Now, different objects would have different ways on how they would handle electromagnetic radiation. For opaque solids, we know that they don't let light through, so therefore its transmissivity is equal to 0. And for perfect black bodies, we know that black bodies absorb all of the radiation directed towards it. Therefore, it does not reflect radiation. It also does not transmit radiation. Therefore, for black bodies, both of those parameters are 0. We are left with alpha, or absorptivity, is equal to 1. Now, Kirchhoff's law states that for a body in thermal equilibrium, the absorptivity must be equal to its emissivity. Therefore, for black bodies, the absorptivity and the emissivity are both equal to 1, meaning a real black body is a perfect absorber and is also a perfect emitter. Okay? Shown in this figure are the nature of reflectivity, absorptivity, and transmissivity. For the purposes of thermal radiation, we are mostly concerned about absorptivity and emissivity. So while we are talking about black body radiation, we have earlier mentioned that black bodies are perfect emitters and perfect absorbers. Therefore, the emissive power of a black body should be the maximum for that particular temperature. We write that the emissive power of a black body, E sub B, is equal to the Stefan-Boltzmann constant, or sigma in this case, multiplied by absolute temperature raised to the fourth power. Now, if we have a non-black surface, meaning it's no longer a black body, the emissive power is lower than that of a black body, such that if we take the ratio of the emissive power of the non-black surface divided by the emissive power of the black body, we get the parameter epsilon as written here, and this is what we call emissivity. The emissivity of a material serves as a bridge between its emissive power and the emissive power of the equivalent black body. Therefore, we write that the emissive power of any body is equal to the emissivity multiplied by the Stefan-Boltzmann constant multiplied by temperature raised to the fourth power. For perfect black bodies, emissivity is equal to 1. Okay? Now, this is the main part of our discussion, heat transfer by radiation. The governing equation for heat transfer by radiation is given here, that is Q is equal to A epsilon sigma times T raised to 4 minus surrounding temperature raised to the fourth power. A here is the surface area of the emitting body, epsilon again is the emissivity, and sigma is the Stefan-Boltzmann constant. In standard SI units, the Stefan-Boltzmann constant takes on the value 5.67 times 10 raised to negative 8 watts per square meter per Kelvin to the fourth power. However, if we want to be consistent with our general equation for rate of heat transfer, just as with conduction and convection, we can write the rate of heat transfer in this form. That is, Q is equal to HA delta T. H in this case is our heat transfer coefficient due to radiation, and delta T is the difference between the temperature of the body and the temperature of the surroundings. And the heat transfer coefficient due to radiation is given in this equation, so we no longer need to use any correlations in order to determine its value, unlike in convection. Okay? Please do take note of these equations. Let's try to solve this example. This is a basic problem that lays the foundation for thermal radiation. The roof of a building has an emissivity of 0.9 and an absorptivity of 0.8 for solar radiation. The sun hits down at midday with an intensity of 300 BTU per hour per square feet. If the temperature of the air and of the surrounding is 80 degrees Fahrenheit, if the wind velocity is negligible, and if no heat penetrates the roof, what is the equilibrium temperature of the roof? For this problem, since there is no given area of the roof, we are going to assume that we are dealing with 1 square foot of area of the roof. Here are the given data for our problem. So we assume that we have a 1 square foot area of the roof. The rate of heat transfer coming from the sun is 300 BTU per hour per square feet. The surrounding air temperature is 80 degrees Fahrenheit, and we are given the emissivity and the absorptivity. And we are required to solve for the equilibrium roof temperature. For our solution, we start with a heat balance. A heat balance in this case would look like Q in is equal to Q out, wherein Q in is the energy coming from the sun directed towards the roof, and Q out is the energy that is being emitted by the roof. Okay? So Q in is simply 300 BTU per hour per square feet, but we have to multiply this with the absorptivity. Remember that your absorptivity is only 0.8, meaning that the roof only absorbs 80% of the incident energy. So we have to multiply 300 by 0.8. That is our Q in. For our Q out, we will be using our rate of heat transfer equation for radiation. That is, Q is equal to area, emissivity, Stefan-Boltzmann constant, times temperature of the roof raised to the 4th power minus the temperature of the surroundings to the 4th power. Substituting, we have an area, 1 square foot, emissivity of 0.9, multiplied by the Stefan-Boltzmann constant in English units, that is 1.714 times 10 raised to negative 9 BTU per hour per square feet per Rankine to the 4th power. And then multiplied by the temperature of the roof to the 4th power minus the surrounding temperature is 80 degrees Fahrenheit in Rankines, that is 540 Rankine raised to the 4th power. So from this equation, we can already solve for the equilibrium temperature of the roof. Now, one thing to remember is that this equilibrium temperature only takes radiation into account, and it does not account for conduction and convection. For this to be accurate compared to a real-life system, it has to incorporate convection. Okay? Let's first solve for this. We can use the shift-solve function of our calculator to solve for our equilibrium temperature. That would be 300 times 0.8 equal to 1 times 0.9 times the constant 1.714 times 10 raised to negative 9 times our unknown is the roof temperature, that is x raised to the 4th power minus 540 raised to the 4th power. Shift solve, we get a roof temperature of 700 Rankine. Now, this temperature of 700 Rankine, when converted to Fahrenheit, is 240 degrees Fahrenheit. This is already above the boiling point of water, so this is a very hot roof. But this example does not seem realistic because, again, we have left out the effect of convection. If the temperature of the roof is 240 degrees Fahrenheit and the surrounding temperature is 80 degrees Fahrenheit, there would be an effect if we include natural convection in our solution here. Okay? Natural convection in this case would be another way for the roof to cool off or to lose some of its absorbed energy. In other examples, we will be explaining the solution when radiation and natural convection are both contributors to the rate of heat transfer. Okay? But for now, this problem is meant to show you how do we use the rate of heat transfer equation for radiation. Let's proceed. We will now be discussing view factors. View factors are an important aspect of radiation as the quantity of heat emitted or absorbed by a body is highly dependent on its surface area. And the determination of view factors can help us in simplifying the solutions for radiation. The view factor F12 can be thought of as the fraction of area 2 that area 1 can see. So this is all about if a certain surface can see another surface or can it see itself or vice versa. Okay? Let us illustrate the determination of view factors for this example. Imagine we have a small cube suspended inside of a sphere such that the outer surface area of the cube is A2 and the inner surface area of the sphere is A1. Now we want to know the values of F11, F12, F21, and F22. F11 means the fraction of area 1 that area 1 can see. Basically, if you're looking for F11, you are asking yourself, can area 1 see itself? Now, based on this example, area 1 can definitely see some of its parts because as you can see, we can draw straight lines from one part of the sphere to another part of the sphere without hitting the square. That is our definition of seeing your own surface area. Okay? So we say that F11 definitely has a value, but we don't know that value yet. Now let's first move on to F12. F12 indicates the fraction of area 2 that area 1 can see. So from area 1 to area 2, it is quite clear that area 1 can see all of area 2 because we can draw straight lines coming from area 1 straight to area 2. Okay? So to summarize, area 1 can see two types of area. Area 1 can see itself, and area 1 can also see area 2. That's why we say that if we add F11 and F12, we should get a value of 1, and 1 is the maximum value for a view factor. You can think of view factors as a fractional number that we multiply to area to modify our area term in our rate of heat transfer equation. Okay? So to recap, we know that F11 plus F12 is equal to 1. How about F21? F21 simply means that the fraction of area 1 that area 2 can see. As you can see in this figure, area 2 can see the entire area 1 because we can draw straight lines from the cube to the sphere at any point of the cube. Therefore, we say that F21 is equal to 1. And finally, F22. F22 is the self-view factor of area 2. This means that the fraction of area 2 that area 2 can see. As you can see from this figure, the cube cannot see its own surface. That's why our value of F22 is equal to 0. Okay? Now, since we know the value of F21 that is equal to 1, we can convert F21 to the value of F12 using what we call the reciprocity rule. The reciprocity rule states that area 1 multiplied by F12 should be equal to area 2 times F21. If we know the value of F21, that's equal to 1, and we know the values of A1 and A2, we can simply solve for F12. And once we have solved for F12, we can then subtract that from 1 to get the value of F11. So the values of F11 and F12 here are very dependent on the areas of A2 and A1. Since we were not given any areas for this example, we can just conjecture that F11 plus F12 is equal to 1, and F21 is equal to 1, F22 is equal to 0. Let's try to apply these view factors in another example. We have here two surfaces, a hemisphere and a flat circle. We want to determine the view factors F11, F12, F21, and F22. When you are presented with these types of problems, you first have to determine which among these view factors would be equal to 1 or would be equal to 0. If you take a look at surface 2, you can imagine this as a flat plane. And the interesting thing about flat planes is that they cannot see themselves. That's why our F22 here instantly becomes 0. We say that surface 2 cannot see itself and surface 2 can only see surface 1. With that, we also know that F21 is equal to 1 because the fraction of area 1 that surface 2 can see is equal to 1. Okay? Surface 2 can only see surface 1. So we now have deciphered two values, that is F22 is equal to 0, F21 is equal to 1. Now, if you take a look at F11, this definitely has a value because surface 1 can see itself. We can draw a straight line from one point of the hemisphere to another point of the hemisphere. Okay? So we just have to decipher what is the exact value of F11. Now, just like in the previous example, F11 plus F12 would be equal to 1 because surface 1 can see itself and it can also see surface 2. Okay, let's solve for F11 and F12. Since we now have established that F11 plus F12 is equal to 1, we can simply solve for one of the two variables in a separate equation in order for us to obtain the other one. And in this case, it would be easier to solve for F12 using our reciprocity rule. Our reciprocity rule states that A1 multiplied by F12 is equal to A2 times F21. Area 1 is simply the surface area of a hemisphere, and then area 2 is simply the area of a circle. From the figure, we know that the radius of the circle and of the hemisphere is r sub o. So we write area 1 as 2 pi rho squared multiplied by f12, which we are trying to solve for the value, is equal to area 2, which is pi rho squared multiplied by f21. F21, as we have determined earlier, has a value of 1. From here, we can now solve for f12, which is simply equal to 1 half, or 0.5. And then from our initial relationship, we can now determine that the value of f11 is also equal to 1 half. Therefore, we can say that out of all the surfaces that area 1 can see, half of its vision would go to itself, and half of its vision would go to surface 2. In terms of radiation, we can also say that half of the radiation that is being emitted by surface 1 is being reabsorbed by surface 1, while the other half gets redirected to surface 2. Okay, that is how we interpret view factors. Another fact about view factors that you might find interesting is that the summation of the view factors for a particular surface in an enclosed surface is equal to 1. That's why the summation of the view factors for surface 1 is equal to 1, that is F11 plus F12 is equal to 1, and the summation of the view factors for surface 2, that is F22 and F21, is also equal to 1. Okay, but that only applies for enclosed surfaces. Let's proceed. Given here is the analytical definition of a view factor. So view factors can be solved by this equation. We have a double integral which takes into account all of the areas that can be seen by a particular area. However, this approach is very tedious, especially if we have to solve lots of problems involving view factors. So instead of using this long equation to determine the view factor, we will be using graphs to easily determine its value. Okay? And once we have the value of the view factor, we can easily insert that to our rate of heat transfer equation. This now becomes the rate of heat transfer, Q12, is equal to the view factor F12 multiplied by the area of the emitting body, that is A1, times emissivity, Stefan-Boltzmann constant, and the differences in temperatures raised to the fourth power. Now you can see that the subscripts here are very important. Our Q12 here indicates the rate of heat transfer from area 1 to area 2. And then we have the fraction of radiant energy leaving area 1 that is being absorbed by area 2. Okay? The subscripts of the view factor and the rate of heat transfer must be the same. Now, let's take a look at some of the graphs that we can use to determine the value of the view factor F12. This is an example of such graph. In this case, we have two surfaces, wherein the first surface is a differential surface and the second surface is rectangular with dimensions L1 and L2. The separation between the differential surface and the rectangular area is defined as capital D. Okay? How do we use this graph? We simply solve for D over L2, which is the distance between the two surfaces divided by the length of the rectangular surface. That would be your y-axis value. On your x-axis value, we need to solve for D over L1, which is the distance between the two surfaces divided by the width of the rectangular surface. And then the intersection of those two values will determine the view factor. The values of the view factor are what's being shown here as diagonal lines and curved lines. In some instances wherein the intersection between the x and the y-axis do not fall within these lines, we have to graphically interpolate. Okay? There will be an example later that makes use of this graph, but let's go through some of the graphs first. This is another system wherein we have two adjacent rectangles that are perpendicular to each other. So our area 1 here is the horizontal surface and then area 2 here is the vertical surface. Okay? They have to be perpendicular with each other. And then area 1 is the area on which heat transfer equation is based, meaning area 1 is the one emitting radiant energy. We have two parameters that we have to consider here, capital Y and capital Z. Capital Y is simply the width of the lower rectangle divided by x, which is the length of the rectangle. And then capital Z is simply the width of the second surface divided by the length of the second surface. If you know the value of Z, you can take a look at this x-axis, the value of Z, and then project it upwards to the value of your Y. So this curves given on the graph here shows you different values of Y. Let's say, for example, our value of Y is 0.2 and our value of Z is 6. You simply look for the intersection of those two curves, and then you see that the value on the y-axis or the view factor f12 has a value of 0.4. Okay, that is how we utilize this graph. Next, we have another system wherein we are now considering parallel equal planes. Parallel equal planes, meaning that you have two planes that are parallel with each other, separated by a distance d. The view factor is on the y-axis, and these different curves here have different meanings. First, we use curves 1, 2, 3, and 4 for direct radiation between two planes. We use curves 5, 6, 7, and 8 for planes connected by non-conducting but re-radiating walls. We use curves 1 and 5 for disks or circles. We use curves 3 and 7 for 2:1 rectangle, or the length is twice the width. We use curves 2 and 6 for squares, and curves 4 and 8 for long, narrow rectangles. Okay? We simply have to determine the ratio, which is the smaller side or diameter divided by the distance between the two planes. So if we have two rectangles that are parallel to each other and they are separated by a distance d, the ratio is simply the width of the rectangle divided by the distance d. Once you find the value of the y-axis, you simply project it towards your chosen curve depending on the system, and then you can now read the value of the view factor here. Next, we have the view factors of parallel disks of unequal size. Our previous graph is only useful if your two surfaces that are parallel with each other have the same dimensions. If the two disks are no longer of the same size, we may use this graph. In the y-axis, we have the view factor f12. On the x-axis, we have the ratio d, or the distance between the two disks. And the lines that are inside of the graph are the ratio r2 over d. This is just a typo, okay? r2, or the radius of the second disk, divided by the distance d. So you first solve for d over r1, that's your value for the x-axis. Locate the value and then project it upwards until it intersects to your value of r2 over d, and then read the value of the view factor from there. Next, we have the view factors for concentric and coaxial cylinders. These are cylinders that are nested within each other, which share the same axis. For this system, we could either solve f21 or f22. f21 is the view factor representing the fraction of the radiation coming out of area 2 that is being absorbed by area 1, and then f22 is the self-view factor, okay? Because area 2 will also be able to see some of its area. For these graphs, we just have to determine the ratio of the radii, that is the smaller radius over the bigger radius, and we also need to determine the length over radius ratio. L is simply the length of the cylinders, and that will be divided with the radius of the larger cylinder. Okay, let's try to solve these examples. Number 1, determine the view factor from a 1 meter square to a parallel rectangular plane 10 meters by 12 meters centered 8 meters above the smaller square. So this is a case of the first system that we have presented earlier, wherein you have two parallel surfaces and one is a differential area. Here are our given. For this example, we simply have to determine d over L1 and d over L2 before we proceed to the graph. Okay, so d over L1 is 8 meters over 10 meters, that is 0.8. And then d over L2 is 8 meters over 12 meters. This is 2/3 or 0.67. Now, we simply have to look for the intersection of these two values in our graph. Let's take a look at the graph. Here we have our graph. So let's first look for the y value, that is d over L2, 0.67. It's somewhere in here, 0.67. And then for the x value, that is 0.8, it's somewhere in here. So we simply have to look for the intersection between these two lines. So based on our projection, the value of f12 is 0.16. That is how we utilize those graphs in order to determine the view factor. Let's have the next example. Determine the view factor of two disks parallel to each other. The smaller disk has a radius of 2 centimeters And the other disc has twice the radius of the other, and they are spaced 1 centimeter apart. So the smaller disc has a radius of 2 centimeters, and the other disc has a radius of 4 centimeters. This is a side view of our system. Now, before we can use the graph, we first have to determine the ratios d over r1 and then r2 over d. d over r1 is simply 1 cm over 2 cm, that is 0.5. And then r2 over d, that is 4 cm over 1 cm, that is 4. Let's go to the graph. Our d over 1 value is 0.5, so it's here between 0.4 and 0.6. And then for our inside line, r2 over d, we have a value of 4. So this is our curve for an r2 over d value of 4. Now we have to look for the intersection between this curve and the x value of 0.5. This is our intersection of the two lines. Now we simply have to read the value of f12. The value of f12 is just slightly above 0.9, so let's just call that 0.91. That is our simple approach in determining the view factor for certain geometries. Okay, let's move forward. Let's now talk about radiation between non-black surfaces. Non-black surfaces, or as we call them, gray bodies, could vary in their ability to reflect and emit radiation. Our rate of heat transfer equation is now written as Q12, or the rate of heat transfer from body 1 to body 2, is equal to the surface area of body 1 times the Stefan-Boltzmann constant multiplied by fancy F12 multiplied by the difference in temperature raised to the 4th power. The fancy F12 now includes the view factor F12, which was previously in our heat equation, and it also includes emissivities of the two bodies that are exchanging heat. That is emissivity 1 from the body emitting radiation and emissivity 2 from the body receiving the radiation. Fancy F12 is what we call the overall interchange factor. For certain applications, it is easier to first determine the overall interchange factor before substituting that to our heat equation given here. Also, for this overall exchange factor, since it contains the view factor F12, you can simply determine the view factor using the graphs that we have presented earlier, substitute it here, along with the emissivities of the two bodies, then you would now have a value of the overall interchange factor, which can be substituted to our heat equation. Here are some more cases wherein you might need to find for the view factors for different geometries in enclosures. This is for non-black surfaces as well. So we have here case 1, 2, 3, and 4. The view factor F in this case is solved as the determinant of this 2 by 2 matrix. The determinant of a 2 by 2 matrix is simply the difference between the product of its diagonals. Okay, this figure is also given in our handbook. Let's have this example. Two parallel planes measuring 2 meters by 2 meters are situated 2 meters apart. Plate 1 is maintained at a temperature of 1100 Kelvin and plate 2 is maintained at 550 Kelvin. Determine the net heat transfer from the high temperature surface under the following conditions. First, the plates are black and the surroundings are at 0 Kelvin and are totally absorbing. Second, the plates are black and the walls connecting the plates are re-radiating. And lastly, the plates are gray with emissivities of 0.4 and 0.8 respectively with black surroundings at 0 Kelvin. Here are our given to the problem. So we have two square plates spaced at 2 meters apart, each plate measuring 4 square meters in area. The first plate is at 1100 Kelvin and the second plate is at 550 Kelvin. It was importantly stated that the surroundings is totally absorbing, meaning it's a black body, and it is at 0 Kelvin. And we are required to solve for the net rate of heat transfer from plate number 1. We will call that Q1 net. Now, you might be wondering, why am I solving for Q1 net when there are only two surfaces, so I should be solving for Q12 instead? Well, Q12 is actually part of Q1 net. We write Q1 net as the sum of Q12 and Q from the first plate going to the surroundings. Because the heat emitted from plate number 1 does not all go to plate number 2. If you would go back to our discussion of the view factors, some of the heat that is being emitted by plate number 1 will be absorbed by plate number 2, while some of the heat will also be absorbed by the surroundings. Okay? If we further expand our expression for Q1 net, we will have Q1 net is equal to Q12 is simply F12, or the view factor from plate 1 to plate number 2, multiplied by the area of the first plate times the emissivity times the Stefan-Boltzmann constant multiplied by T1 raised to the fourth minus T2 raised to the fourth power. This is for Q12. While for Q1 surroundings, this will be the rate of heat transfer from plate number 1 to the surroundings. The view factor from plate number 1 to the surroundings is simply 1 minus F12 because the heat being emitted by plate number 1 can only go to either the surroundings or plate number 2. Okay? And the summation for all view factors coming from one surface is equal to 1. This is multiplied by area 1, emissivity, the Stefan-Boltzmann constant, and T1 raised to the fourth power minus the temperature of the surrounding raised to the fourth power. That's why you were given the information that the surroundings are at 0 Kelvin. With that, T surroundings is simply 0. Okay? This is now your Q1 to the surroundings. The summation of these two terms will be the net rate of heat transfer coming from plate number 1. Okay? For the first case, it was stated that both plates are black and that the surroundings are totally absorbing. Therefore, we say that the emissivity for the first case is equal to 1. Now, we simply have to solve for the view factor F12. If we know the value of F12, we can now solve for Q1 net. Okay? So how do we solve for F12? We are going to use one of our previous graphs in which we have two parallel equal surfaces. If we go back, this is the graph that we will use for this problem. Okay? If you take a look at curves 1, 2, 3, and 4, those are for direct radiation, which is our first case. And our system consists of two equal square plates. So for square plates, we use curves number 2 and 6. Curve 2 is for direct radiation. Curve 6 is when you have a non-conducting but re-radiating wall. So let's have curve number 2. We only need to look for the ratio. Now, the ratio is the smaller side or diameter divided by the distance between the planes. Our smaller side is the side of the square, that is 2 meters. And the distance between the two squares is also 2 meters. Therefore, our ratio is simply equal to 1. So if our x value is equal to 1, we simply look for the intersection of x is equal to 1 to curve number 2. Here is that intersection. And then we look for the y value for the view factor F12, that is 0.2. Going back, we can now substitute our given to our derived net rate of heat transfer by radiation. That is F12, 0.2 times A1, 4 square meters. Emissivity is 1. Stefan-Boltzmann constant, 5.67 times 10 raised to negative 8, multiplied by T1 is 1,100, that's raised to the fourth power, minus T2 is 550, that's raised to the fourth power. So this value we have here, 62,000 kilowatts, is the net rate of heat transfer from plate 1 to plate 2. Now let's add the contribution to heat transfer from plate 1 to the surroundings. That would be 1 minus F12, that is 0.8, times A1 is still 4, emissivity is still 1, Stefan-Boltzmann constant, T1, 1,100 raised to the fourth power. The temperature of the surroundings is at 0 Kelvin. This is our answer for Q1 net, that is 327.9 kilowatts. Based on all of the conditions on this problem, the net rate of heat transfer coming from plate number 1 is equal to 328 kilowatts. That is if the space between plates 1 and 2 are empty. Now let's move to the next question. For the second case, the plates are black and the walls connecting the plates are re-radiating. So you would notice that for letter B, it was not stated that the surroundings are at 0 Kelvin and are totally absorbing. With this, it is understood that we are only interested on the net rate of heat transfer from plate 1 to plate 2 because there's not enough information about the surroundings, okay? The solution to part B is similar to that of part A. We just need to get the first term of our heat equation. Here, instead of solving for the net rate of heat transfer Q1 net, we will only be solving for Q12. And based from our overall equation, Q12 is simply F12 A1 emissivity constant times the difference in temperatures of the plate raised to the fourth power. Okay? But with that, we still have to note that our plates are black. Therefore, emissivity is still equal to 1. But the value of the view factor F12 will change because for this instance, the space in between the two plates now have a non-conducting but re-radiating wall. Okay, and that will change the value of our F12. If we go back to our graph, for planes connected by non-conducting but re-radiating wall, we use curves 5, 6, 7, and 8. And then for squares, we are going to use curve number 6. So you only need to locate curve number 6 and then take a look at its intersection with the ratio or the x value. Our ratio in this case, or our x value, is still equal to 1 because there were no changes to the geometry of our system. So if we take a look at the intersection between x is equal to 1 and curve number 6, we have this point right here. And then project that to the y-axis, we now have the value of the view factor F12. We estimate that as 0.53. Now we can substitute everything to the first term of the heat equation because again, we are only looking for the transfer of heat between plates 1 and 2. View factor is 0.53. Multiply that with area, 4 square meters. Emissivity is equal to 1. The Stefan-Boltzmann constant. And then the difference in temperatures, 1 raised to the 4th power minus 550 raised to the 4th power. Our rate of heat transfer from plate 1 to plate 2 if they are connected with a non-conducting but re-radiating wall is 165 kilowatts. For the third case, the plates are gray with emissivities of 0.4 and 0.8 respectively with black surroundings at 0 Kelvin. The statements with black surroundings at 0 Kelvin means that we have to include our second term, which is the rate of heat transfer from plate 1 to the surroundings. Okay? So for letter C, we will use the entire form of our Q1 net equation. However, since the plates are now gray, we are going to use emissivity 1 of 0.4 and emissivity 2 of 0.8 in our overall interchange factor, fancy F12. Okay? So let us first solve for the overall interchange factor, and then we will go back with our net heat rate equation. This is our equation for the overall interchange factor. We simply have to substitute our view factor F12. Now, the view factor F12 is the same as that of letter A, that's 0.2, because there was no mention of a non-conducting but re-radiating wall in between the two plates. Okay, so F12 is 0.2, emissivity 1 is 0.4, emissivity 2 is 0.8, area 1 and area 2 are both 4 square meters because we have two parallel equal squares. Okay, substituting. Our overall interchange factor is 0.148. Now we have to modify our Q1 net equation a bit because the overall interchange factor already includes the view factor F12 and the emissivities. We do need to solve for another overall interchange factor. We will call that fancy F1 surroundings because again, plate number 1 is still exchanging heat with the surroundings at 0 Kelvin. Okay? Now, for the evaluation of F1 surroundings, we simply have to use emissivity 1 is still equal to 0.4, but emissivity 2 is now equal to 1. If you go back to the equation of the overall interchange factor, you would now see that the modification to this equation would become fancy F1 surroundings is equal to 1 over the view factor from surface 1 to the surroundings plus the following. But if you take a look at this ratio, A1 over A2, A1 pertaining to the area of plate 1, and then A2 pertaining to the area of the surroundings, we can say that the area of the surroundings is much more bigger than area 1, such that the ratio of A1 over A2 approaches 0. If A1 over A2 is approaching 0, meaning it's a very, very, very small number, we can neglect this term such that we will only be left with 1 over F1 surroundings plus this following terms. Okay? Let's compute 1 over the view factor from plate 1 to the surroundings. That is simply 1 minus 0.2 because remember 0.2 is the view factor from plate 1 to plate 2. So that is 1 over 0.8 plus the quantity 1 over emissivity of plate number 1. That's 0.4 minus 1. This is now our overall interchange factor between plate number 1 and the surroundings. That is 0.364. Okay? Now, we do have to modify our Q1 net equation because remember that the overall interchange factor already includes the view factor and the emissivities. We can now rewrite our Q1 net expression to be overall interchange factor 1, 2 multiplied by area 1 times the Stefan-Boltzmann constant T1 to the 4th minus T2 to the 4th power. plus for the second term, that is overall interchange factor, F1 surroundings times A1 times the constant multiplied by T1 to the fourth power. Because remember that our surroundings are still at 0 Kelvin. Substituting, we have F1 2.148 times area 1 is still 4 square meters times the constant times the difference in temperatures. It's 1 raised to the fourth power minus 550 raised to the fourth power. So the contribution of Q12, or the rate of heat transfer from plate 1 to plate 2 to the net rate of heat transfer, is 46 kilowatts. We then add the contribution of the rate of heat transfer from plate 1 to the surroundings. That is, overall interchange factor F1 surroundings, that is 0.364 times area times the Stefan-Boltzmann constant times 1,100 raised to the fourth power. Our net rate of heat transfer, Q1 net, is therefore 166.9 kilowatts. So that is how you solve problems involving radiation for black and non-black surfaces. It is very important for you to understand the problem because the context of whether you are solving for a direct heat exchange between two surfaces or the involvement of multiple surfaces will be discussed in the problem itself. Okay? That's it for the basics of radiation heat transfer. Please do watch out for a separate video detailing the involvement of natural convection and radiation heat transfer and weighing the two together. Which one should be important than the other? Or should both heat transfer coefficients be considered in our overall rate of heat transfer equation? Okay? Thank you for listening, and as always, keep safe.